Okay, so thank you for introduction. First of all, I would like to thank the organizers to organize this great conference. So I'm Kenji Furuya at NAOJ, and along with Martin, we are going to talk about chemical link between planet-forming regions and our solar system based on isotope ratios of volatile elements. And our team is led by Hideko Nomura-san and includes scientists in a variety of different fields. Okay, so our solar system was formed through the gravitational collapse of the molecular cloud core and the subsequent formation of the disk around the young sun. And in the disk, dust grains grow into planetesimals, and planetesimals grow into planets, as discussed in previous chapters. And various molecules, including water and organics, have been detected in molecular cloud and also planet-forming disks. And one of the ultimate goals of astrochemistry and cosmochemistry is to understand how molecules are formed in space and how molecules are supplied to planetary system eventually. And for that goal, isotope ratio of volatile elements are powerful tools. Why? Because isotope ratios are kind of a fingerprint of molecular evolution. And for example, by comparing isotope ratios in objects at different evolutionary stages, we can get insight into molecular evolution during star and planet formation. And since PP6, we have many new observations, such as by ALMA, and also new space missions, such as Rosetta. And we would like to share new such observational results with you. And in the first of this talk, I will discuss the isotope ratios from clouds to disks. And in the second half, Martin will discuss isotope ratio in the solar system. Right? And the key question in my part is whether this chemical composition is inherited from clouds or determined inside disks. So this is a key question in my part. And let's start with the very basic of the isotope chemistry. So we have the measurement of the elemental abundance ratio of isotopes in the solar system and also in the local ISM. So they are not significantly different, but not identical, reflecting the chemical evolution in the galaxy. And if isotopes with given element behave in the same way in chemistry, we should expect that isotope ratio in molecules should be the same in the elemental abundance ratio shown in the table. However, in reality, different isotopes behave differently, and we have, and as a result, isotope ratio of molecules can be deviated from the elemental abundance ratio. So this is isotope fractionation. For example, if we look at the crystal core, D2H ratio of N2H plus can reach 0.1. That is 4 orders of magnitude higher than the elemental D2H ratio, right? So what causes isotope fractionation? So there are two main mechanisms to initiate isotope fractionation. So one of the two is the isotope exchange reaction, and the most important reaction for deuterium chemistry is reaction between H3 plus and HD to form H3 plus and H2. The combination of the H3 plus and H2 is energetically more stable compared to the combination of H3 plus and HD by around 200 K. And due to this energy difference, the reaction in the forward direction, right direction, is much faster than the reverse direction. And as a result, D2H ratio of H3 plus becomes high compared to elemental D2H ratio, and such high D2H ratio of H3 plus propagate into other gas phase species and icy species through various chemical reactions. So this is the explanation for deuterium chemistry, but in general, isotope exchange reactions move the chemical system into energetically favorable direction. So this is a general rule. And isotope exchange reactions are more efficient at lower temperatures because if temperature is high, energy difference between different isotopologues does not matter anymore. Okay? So another mechanism is isotope selective photodissociation. So let's consider N2 photodissociation as an example. So if we consider a molecular cloud illuminated by UV radiation from the top side, at some depth, UV radiation, which can dissociate 40N2, is attenuated. due to the absorption by 40N2 itself. So this is so-called self-shielding. And you may know the self-shielding by H2 molecule. It's same. However, in the case of 50N, 40N, the situation is a bit different because 50N, 40N is much less abundant compared to 40N2. So as a result, in the self-shielding region of 40N2, 50N, 40N is selectively photodissociated, producing the excess of 50N atoms compared to 40N atoms. And such abundant 50N atoms can be used to produce N-binding molecules such as ammonia and HCN. And as a result, 50N enriched molecules are formed. So similar mechanisms affect oxygen and deuterium fractionation chemistry through CO photodissociation and H2 photodissociation. So I would like to stress that these elemental chemical processes are well studied thanks to the quantum chemical calculation and also laboratory studies, right? So there are two main mechanisms to initiate isotope fractionation, and we can distinguish them by observing the spatial distribution of isotope ratio in the ISM. So this color map shows the carbon density ratio of HCN to HC50N in prestellar core L5044. And in this core, in the south part, the ratio is lower compared to core center and north part, meaning that in the south part, HCN is enriched in 50N. And in this core, it is known that south part is efficiently illuminated by UV radiation compared to core center and the north due to the lower visual extinction. So this map is very consistent with that nitrogen isotope fractionation is caused by isotope selective photodissociation rather than exchange reaction. And how about deuterium chemistry? So here is a map of the C3HD emission and the C3H2 emission in the same core. If we look at the C3HD emission, the emission peak corresponds to the dust continuum peak. On the other hand, C3H2 emission is offset from the dust continuum peak, meaning that D2H ratio is highest in the core center. So this is different from the nitrogen isotope case. And this means that isotope exchange reaction is the main driver of the deuterium chemistry, right? And so we can include isotope fractionation reactions into astrochemical model to predict isotope ratios in molecular cloud and also in disks. So here is an example which shows the isotope ratio along with the main budget of each element in molecular cloud predicted by astrochemical model. And this figure is very messy, and please see our chapter for detail. But basically, model predicts that deuterium and carbon isotope fractionation occur by the isotope exchange reactions. On the other hand, oxygen and nitrogen isotope fractionation occurred through isotope selective photodissociation with some contribution from isotope exchange reaction. And these are basically consistent with observations. However, we need 3 more effort for quantitative understanding. For example, models failed to explain very low 40N to 50N ratio of N2H plus observed in prestellar cores. That is the future work. Okay, so let's discuss about water. We already know that bulk of water is formed as ice in the prestellar environment. And after the protostar formation, envelope is heated up and water ice sublimate into the gas phase in region where temperature higher than 100 K. And we can observe such sublimated water by using Alma and Neumann and measure its D2H ratio as plotted here. Yeah, class 0 sources. So the D2H ratio of sublimated water is around 10 to minus 3, which is much higher than the elemental D2H ratio. And very recently, water D2H inside water snowline over a disk was measured for the first time in outbursting source V8083 ORI and found that D2H ratio is similar to protostellar envelope and also comets in our solar system. And this similarity indicates that water in disk and comets are inherited from the prestellar stages rather than formed inside the disks. And this scenario is also consistent with the model prediction, which traces water DH evolution from clouds to disks. However, we still need disk processing to explain the D to H ratio of water in comets. So there are variations. So why? So one of the possibilities as follows. In the very inner disk regions, let's say temperature higher than 500 K, isotopic exchange between H2 and water occurred efficiently, reducing water D to H to 10 to minus fifths. And in the outer disk, such isotopic exchange reaction is too slow, so water D to H remains to be 10 to minus 3, as observed in protostellar envelope and in disks. And in the disk, the two water sources with different D to H ratio are mixed via radial mixing, making the gradient of water D to H as shown in the left panel. And so the measurement of water D to H ratio in disk is a key to understand the origin of cometary water and also meteorites. And in the case of V8083 Ori disk, inner 40 AU is optically thick in dust, so we cannot observe water in inner regions. So we don't know. And observation of water D to H in class 2 disk is also very important, but would be very challenging because class 2 disk is cold. Okay, so let's go on to organic species. Here we would like to focus on HCN molecule. So this is a simple organics. And we would like to focus this because HCN is a building block of more complex organics. And also, more practical reason is that HCN is one of the most studied species, and various HCN isotopologues have been detected in different evolutionary stages of star and planet formation, so that we can track HCN chemistry using isotope ratio. And actually, HCN is one of the most studied species in class 2 disk from the viewpoint of isotope chemistry. And I'd like to also mention that HCN is much less abundant compared to water. In comets, abundance is 0.1% relative to water. So naively speaking, HCN would be much easily affected by chemistry inside disks. Okay, so this plot shows the 40N to 50N ratio for HCN in different evolutionary stages. So it seems that the 40N to 50N ratio decreases from prestellar core to class 2 disks. And in class 2 disk, both in class 2 disk and comets, HCN is enriched in 50N, so there are some similarities. However, we need some caution when we compare the disk observation and comet, because disk observation basically traces gas, but comet observation basically traces ice. However, so let's think about why in class 2 disk HCN is enriched in 50N. To answer that question, the radial profile of 40N to 50N ratio of HCN in disk are very helpful. So we can consider 3 different scenarios. In the first scenario, if HCN is inherited from the earlier evolutionary stages like water, we would expect the 40N to 50N ratio is constant across the disk. On the other hand, if HCN is formed inside the disk and isotope selective auto-dissociation is at work, we would expect the ratio increase with increasing distance from the star, because the inner disk UV radiation is stronger. And in the third case, if HCN is formed in disk and isotope exchange reaction is at work, we would expect the ratio decreases with increasing distance from the star, because isotope exchange reaction is efficient at cold temperature. So this is a prediction. And recent spatially resolved observation with ALMA allow us to constrain the radial profile of 40N to 50N ratio of HCN in class 2 disks. So the top panel shows the HCN emission map for 2 different disks, and the bottom panel shows the 40N to 50N of HCN ratio in two different disks shown by red colors. So as you can see, the ratio increases with increasing distance from the star. And this trend is very consistent with the prediction by isotope selective photodissociation scenario. So this means that HCN is formed in situ in disks in outer layers of disk being irradiated by UV radiation. Okay, so, and also, if you look at the bottom panel, the 40N to 50N ratio in disk somehow similar to that in comet, at least at some positions. However, as I mentioned earlier, comparison between disk observation and comets are not straightforward because one sees the gas, another sees the ice. But however, one possible scenario is that HCN in the outer disk layers, not the midplane, are vertically transported to the midplane and frozen out onto dust grain and incorporated into comets. So this is just a speculation, but we need a model which considers isotopic chemistry and transport processes inside the disk to test such scenario. Okay, so spatial distribution of D to H ratio for HCN was also measured in some disks. For example, Cataldi et al. 2021, which is one of the MAPS paper, found that the spatial distribution, they found that the outer disk shows a higher deuterium fractionation ratio, which is consistent with the active isotope exchange reactions inside the disk. And also, it suggests that in situ formation of HCN again. They also found that even in the warm region, temperature is around 50 K, D2H of HCN is relatively high, around 10 to minus 2. And if we only consider the H3D plus chemistry, this high ratio is difficult to explain. And we need warm deuterium fractionation pathway like shown in the slide. And they also found that the DH of HCN in disks are typically higher, 10 to minus 2, compared to that in comet, except for inner 50 AU of the Habib A stars. Okay, so 13C fractionation is not well studied compared to nitrogen and deuterium fractionation in disks, but we have some observation toward TW hydra disk. What we know so far is that the 12C 13C ratio for HCN is higher compared to elemental 12C 13C ratio. On the other hand, 12C 13C ratio for CO is lower than the elemental abundance ratio. And recently, Soko Lee and us construct a disk chemical model with carbon isotope, and we found that this trend is consistent with the isotope exchange reaction with carbon to oxygen ratio rather than unity. And we need excess carbon to make that exchange reaction effective. And if we look at comets, comets do not show carbon isotope fractionation. So this is something different from disk observation. Okay, so summary so far. Water in disk and comets are likely inherited in the prestellar stages. And this observation of the disk around outbursting source is very helpful to study isotope ratios because we can see the ice. And ALMA observation allows us to study a spatial distribution of molecular isotope ratios in class 2 disks. And these observations suggest that active isotope fractionation chemistry inside the class 2 disk. And also, spatial distribution is very helpful to understand the origin of molecules. And finally, we need a model which considers isotope chemistry and transport process simultaneously to connect gas observation by ALMA and cometary observation. Okay, so now go ahead, Martin.
Okay, thank you very much, Furuya-san. Okay, great to see so many people still here. I should go quickly, though, I think. So, something's missing off the bottom. Never mind. It's my job to round out this amazing conference, completing our journey from the giant molecular clouds to the smallest bodies in our solar system. Kenji Furuya-san did a great job of explaining the fundamental fractionation processes that occur in interstellar clouds and protoplanetary disks. And it's my job now to go on to explain how those concepts can help us interpret isotopic observations of various different solar system bodies. Now, as you probably know, observations of protoplanetary disk midplanes are extremely challenging, even with the most modern telescopes. So we have to go over to techniques of observing our objects in our own solar system, using, for example, remote sensing of planetary atmospheres and comets, rendezvous interception and in situ missions to solar system bodies, and finally laboratory analysis of samples either collected and returned or delivered to us within meteorites. Comets and indeed carbonaceous chondrite meteorites provide us with some very pristine samples of the processes that occurred during our early solar system and its evolution. They're relatively little modified, and so therefore we can investigate their isotopic compositions to gain insight into processes such as the infall of interstellar matter into the disk. Let's see if I can get a laser. There it is. It's very small. Chemistry within the disk in terms of gas phase ion molecule, as well as grain surface chemistry, photochemistry that we've been hearing about, and also the fundamental physical dynamical processes such as radial and vertical mixing, which can mix things up in different and potentially unexpected ways. So one of the landmark measurements in this field of study was the Giotto mission to Comet Halley, measured the D/H deuterium to hydrogen ratio in water in a comet for the first time through mass spectrometry, and obtained a value which was significantly enriched compared to the sun and the giant planets, and also pretty much everything else in the solar system. And the D/H ratio was found to be pretty consistent with observations of water and D/H in protostars at the time. So this hinted at a significant amount of interstellar material being incorporated directly into comets, which was quite exciting. Over time, we have built up a diversity of comet measurements. We've got 12 different comets and a few upper limits that have D/H measured by now. And we see a significant spread in the values. These are the comets in green. I can't see this laser pointer at all. Basically what I want to highlight here is that comets do seem to be enriched in deuterium compared to the Earth's water, but there is genuine diversity among the comet population. Some have more deuterium than others. And in fact, a really interesting study by List 2019 found that you could correlate the D/H ratio in comets with the active fraction, and that is to say how productive is the comet compared to the size of the comet. More productive comets are producing more water as a result of icy grains in the coma. So what this appears to show at face value is that those icy grains and chunks, which are discovered abundantly around some comets, but some comets don't seem to show them at all, those icy grains may have a different D/H, a lower D/H than actually the bulk nucleus. So this may be evidence for two different reservoirs of water being incorporated into cometary nuclei. The statistics are a little bit limited, however, at the moment. I would say more studies are needed to really investigate and confirm this trend and understand it. Okay, so moving over to look at the nitrogen fractionation. As Kenji said, nitrogen can be fractionated by a couple of different mechanisms, but what you see here on the left is the prestellar cores, which show, in some cases, defractionation, loss of the heavy nitrogen in some molecules, whereas some molecules are slightly enhanced. Protoplanetary disks. Nope, can't see it. protoplanetary disks show a definite enhancement, quite a strong enhancement in the 15N, the heavy nitrogen, the result of isotope selective photodissociation. And that seems to be carried over pretty well into what we see in the comets in our own solar system. They show a pretty similar D over H, and it's actually very uniform. If you want to talk more about comet D over H, come and see me at my poster. It's probably a bit late for that now, but anyway, if you want to talk to me more about that poster, I'm happy to show it to you. So as we move towards the sort of inner solar system, I guess, more towards where the meteorites are coming from, we see that the 15N seems to be getting lost somehow, or at least less enriched. And finally, the planetary atmospheres on the right show a broad diversity of 14 to 15N, which the origin of which I'll talk about later. The oxygen isotopic fractionation is another story that helps us provide another piece of the puzzle on the origin of the materials from which the Earth and other planets formed. We have, before Rosetta, we had a pretty uniform distribution of 16 to 18.0 values, clustering around the terrestrial value of 500. But what Rosetta did was really blew things apart and showed us that there could be very strong oxygen isotopic fractionation in some molecules, like formaldehyde and the sulfur-bearing species, and even in O2. So that provides us with an interesting conundrum and something to attempt to go at with our models. But actually, you can explain in the interstellar mediums this kind of strong oxygen 18 enrichment through 18.0 ion-neutral gas phase exchange processes. Anyway, the overall picture here, I think, is that we have at the moment what appears to be a reasonably good sort of semi-quantitative understanding of the deuterium, the nitrogen, and the oxygen isotopic abundances in comets. What we seem to be seeing is that there's a significant reservoir of interstellar deuterium-rich water that's maybe being mixed in with some slightly less deuterium-rich water, perhaps closer to the proto-sun. And that's also consistent with our picture of comets built up from the stardust samples, where we see these high-temperature minerals, these crystalline silicates formed at high temperature, mixed in with the material accreted at much lower temperatures further away from the sun. The 15N fractionation in cometary volatiles is similar to that found in disks, and this is therefore consistent with isotope selective photodissociation of N2 in the protosolar nebula. And these 18.0 enrichments, as I said, consistent with 18.0 exchange at low temperatures in the cold gas, along with some isotope selective photodissociation of optically thin C18.0 to liberate that 18.0 and give rise to enhanced 18.0 abundances in some of those species that we observe. So I'm going to move on to talk about meteorites now. These are really fascinating, and it's not my area of study. So I'm going to try and distill an entire field of research down into 5 minutes. I'm bound to make a few mistakes, so I apologize for that. So the carbonaceous chondrite meteorites provide us with a record of the material that was accreting in the solar system just a few million years after its evolution. We could tell that from the isotopic ratios. These carbonaceous meteorites accreted silicates, metals, organic matter, and most of them also accreted quite large amounts of water, now, as well as the complex organics. Now, because of the heating, as explained by Steve Desch in his talk, there was 26 aluminium contained in these asteroids, and this allowed the larger ones particularly to get very hot and melting the water and leading to aqueous alteration and some thermal alteration of these materials. So if we look at the D over H ratios in meteorites, Conor Alexander led a significant body of work to analyze the water content in meteorites. There's no water left in actual sort of liquid form in these meteorites, but they leave behind a lot of hydrated minerals and clays in the meteorites, and analyzing the D over H in those tells us what the water was doing. And you see over here on the left, the meteorites, the carbonaceous chondrites are plotted in green, and they show a significant spread, but predominantly values clustering around the terrestrial value, and in some cases a bit lower. So what's going on there? It appears like, yeah, we've got this D over H rich water being incorporated and likely being mixed in to varying degrees with isotopically equilibrated water from closer towards the protosun. But there's some outliers here, and it's quite peculiar to see ordinary chondrites and the rumarutes very enriched in deuterium. And this can be explained as a result of aqueous alteration. In fact, if you react water in the liquid phase with iron in the meteorites, you release H2. The H2 fractionates strongly with the water, and you get deuterium-poor H2 being released, while the water in the meteorites ends up becoming progressively deuterium-enriched. So that explains what we see there. Meanwhile, the organics, upon aqueous alteration, actually become less deuterium-enriched because they're undergoing DH exchange with the relatively deuterium-poor water. So we go from this case of the very deuterium-rich organics in 67P, and then aqueous alteration in the disk gives rise to this sort of spread and reduction as we increase the aqueous alteration and reduce the amount of hydrogen. The nitrogen in meteorites tells a slightly different story of the organics, but again, it's consistent with what we believe is the paradigm of isotope selective photodissociation in comets, providing the source of the nitrogen. And we have a spread of 14N to 15N values. Many of them cluster around the terrestrial value. And this diversity is probably as a result of variations in the 14N to 15N ratio in the disk as a result of these sort of isotope selective photodissociation effects, which are radially dependent, as Kenji showed in this talk. So we can explain this kind of diversity through those models. The oxygen 18 and 17 isotopes tell us the story of the water, and the silicates in the solar system, again, the values cluster around the terrestrial value, but they all lie along this mass-independent fractionation mixing line. Mass-independent fractionation means that the degree of fractionation of the 17O and the 18O is pretty similar and doesn't depend strongly on the mass. So the more fractionation we have in one, we have more in the other. And so this kind of mass-independent fractionation implies the mixing of material enriched in both 17O and 18O isotopes. And this can be explained as a result of production and enrichment in both of those isotopes of oxygen after our good old friend isotope selective photodissociation of CO. And then if we get this 18O enriched water and mix it down into the protoplanetary disk mid-plane, it can then undergo isotopic exchange with the silicates to produce the enrichment that we observe. So I'll just try and round things off with a discussion very quickly of the planetary atmosphere observations. Here we see 4 examples of planets with pretty substantial atmospheres, and therefore some of the easier ones to study. Venus, Earth, Mars, and Titan. If we look at the isotopic enrichments in deuterium, carbon, nitrogen, oxygen, we see that particularly deuterium, things vary really wildly, and this is basically showing us the effects of the atmospheric loss of the light isotope. The nitrogen story is a bit more complex, and I'll get onto that. So Titan provides us with a really interesting example case to investigate what's going on with the nitrogen. Here we see observations from Cassini and ALMA of the different isotopic ratios in various molecules on Titan, in Titan's atmosphere. Well, we don't see a whole lot of fractionation in the carbon, so as tends to be pretty common throughout the solar system, carbon-13 is not very enriched or depleted. D over H is fairly close to the terrestrial value, but there does seem to be some fractionation going on in Titan's atmosphere. I need to speed up. Yeah, so that may be a result of preferential loss of H atoms compared to D during or fractionation during photodissociation of methane. The nitrogen is the really interesting one, and this shows quite a strong enrichment compared to the terrestrial value, and is quite similar to the comets, the 14N to 15M ratio, and therefore shows us that the ice was formed in probably a similar way to the cometary ice, or comes from a similar reservoir accreted within the Saturnian subnebula. We end up with isotopic enrichment of the photochemical products on Titan as a result of isotope selective photodissociation of N2 in Titan's upper atmosphere. So the nitrogen 15 molecules, atoms get released into the gas phase preferentially, and then incorporated into Titan's photochemical products. We then have to consider loss of those products to the surface through precipitation, and also loss of the 14N at the top of the atmosphere. These are some Almar observations I did showing those isotopologues of HC3N. Very quickly, Mars, well, this is another great example of these processes in action. There's some data obtained from ground-based studies with the Keck and IRTF telescopes. The D over H value on Mars is extremely high. It varies from typical values of 5 to 10 times terrestrial, whereas actually it seems to be depleted, relatively speaking, at the poles. And this can be explained as a result of preferential sequestration of the heavy water at the surface. So there's a slight difference in the condensation temperature of deuterated versus non-deuterated water, and that means that the heavy water tends to freeze out more readily at the winter poles, and that can explain this diversity. But the overall very high D over H on Mars is a result of this dramatic loss over billions of years of Mars's atmosphere, and preferential loss of the light isotope. So we have to consider all these processes if we're going to understand the evolution of isotope ratios in planetary atmospheres. Here's just an overview of many of the different escape processes that differentially affect the heavy versus light isotopes. We're talking about loss preferentially of the light isotope, and then preferential sequestration in many cases of the heavy isotope at the surface. So we have to consider the balance of these processes if we're ever going to wind back the clock to get at the original isotopic compositions of planets. I'm not going to talk about this. We know JWST is great. It's going to do great things. The spectra are going to be amazing. So, another missing figure. Yeah, I think I'll just leave my summary up there. I've spoken long enough already. Thank you very much for your attention.
Thanks a lot. Trying to wrap this complex story up in such a short time. The floor is open to questions to both Kenji and Martin. Can you please line up behind the microphones? Yes, please. Let's start there.
Yes. Hello. Yes, it's a question about the second part of the talk, and if you could show slide 24 on the nitrogen isotopes. It relates to a little bit what I talked about this morning. Maybe you had a slide with the nitrogen isotopes in the pre-solar cores and pre-stellar cores. Yeah, that one, disks. And the question is really, how do we accrete nitrogen on Jupiter and Saturn? And I see that in disks you have values here that are quite low. And I was wondering where they are measured. Is that in solids? And if it's the case, do you have the possibility to measure that in very cold disks, where N2 would condense?
Yeah, I'm not sure if the exact form of the nitrogen incorporated into Jupiter is well known. I could say that these values here that you see on this plot, were these, do you remember where they're from exactly, Kenji? These are HCN, the disk. Yeah, so these are the HCN. So yeah, I don't exactly know how Jupiter accreted its nitrogen, but I assume that a lot of it was as N2. So maybe this ratio in disks is not representing the bulk gas; it's representing just the isotopically enriched gas in the organics.
So to make sure this is HCN vapor, but coming from the solids, so it's enriched.
I think it's produced in the gas phase.
So that HCN is coming from the disk surface layer of HCN.
Okay.
So not the solid in the midplane.
Okay.
So that is not representative of the bulk composition, I think.
Okay, thanks a lot.
Okay, so we jump to that side, please, in the back.
Hi, Camber Schwartz, MPIA. My question is for Kenji. So you mentioned that in protoplanetary disks, the D to H ratio of the gas tends to be higher in the outer disk. And you also mentioned that the primary deuteration pathway involves reactions with ions. So do those two things together mean that ionization is likely higher in the outer regions of protoplanetary disks versus the inner? What do you think?
So yeah, I didn't say such kind of thing. So okay, so please go back to the figure. So what I said is in the outer disk region, water is just inherited from the protostellar envelope or something like that. So there is no chemical processing inside the disks for outer disk.
Not for water, for the more complex gas phase species.
Okay, HCN case, you mean? Yeah, so in this case, I just think that the temperature is colder in the outer disk region, so that is the only reason why outer region shows higher D to H compared to inner disk region.
Okay.
And we don't know the ionization rate from this observation, I think.
So Evie, please.
Evie van Nishoek, Leiden. So thanks for putting all this information together. That will be very useful as a reference to check. I was actually interested in your new results on the 12CO over 13CO in this, and especially how you can get this rather puzzling low value that is also now being observed in planetary atmospheres of 12CO over 13CO, which is on the low side rather than on the high side.
Okay, so for the low 12C 13C of CO in disk, we need an isotopic reaction with carbon to oxygen ratio rather than unity.
But is this in the midplane or is this in the disk surface layer?
So I think it's just above the CO snow surface.
Oh, so you don't know yet what it is going to be in the ice?
No, we don't know.
Planets may be built.
No,
okay,
no.
Good. Thanks. That will be interesting to study as well.
Yeah, and in the link to the planetary atmosphere of 12C 13C ratio, so in the T double hydra disk, carbon abundance is very low. So I do not think there is a direct link because carbon is poor in this disk. Yeah.
Okay. Thanks.
Okay, we move all the way to the right.
Mordecai Maclow, AMNH. So we're comparing 5 gigayear-old planetary system here to modern protostars. Has there been sufficiently low galactic chemical evolution and radial drift of the sun that's a legal comparison? Or are these variations actually just telling us that we moved to a different neighborhood at a different time?
So so we need to take care of what is the elemental abundance ratio, and we need to care about the difference of the isotope ratio between the solar system and the current ISM. And so we can go back to this one. So if we consider the D to H ratio, its two value is close, and and the enrichment of D2H ratio is order of magnitude, so the difference between the two is negligible, I think. And the most problematic thing is nitrogen. So yeah, abundance ratio in the current ISM is much lower compared to solar system. I think this reflects the galactic evolution, as you mentioned, and also the movement of the sun in the galaxy. So yeah, so the direct comparison of the absolute value of 14 to 15 ratio of molecules between solar system and ISM is not good, I think. So, but we can compare the, let's say, the difference between the elemental abundance ratio and molecular isotope ratio. For example, if the molecules in the ISM is factor of 3 enriched in 50N, and comets in the solar system is also show the similar enrichment factor, we can say that something similar occur. I think that is my thought.
Thank you.
Thank you.
Okay, we have another question over there.
Masanobu Kunitomo at Kurume University. So I'd like to ask the time evolution of the bulk D/H ratio of accreting materials onto the protostar, because deuterium burning is very important for the protostellar evolution. And yeah, in the outer disk, deuterium is trapped in the icy dust grains. So if pebble accretion rapidly pebble accretion occurs, then deuterium is efficiently transported into the inner disk, and the accreting materials would be enriched in the deuterium, and in the late phase, protoplanet is formed and pebbles are blocked. Then accreting materials would be deuterium poor. That was my speculation, but is it true, or?
Okay, so the point would be the how much fraction of deuterium is locked up in H2 and water, and so based on the protostar observation, we know the D2H ratio of water is 10 to minus 3, and water abundance relative to H2 is on 10 to minus 4. So it means the most of deuterium is in H2. So I think the effect of the lateral drift of dust grain is not so significant, much less than the factor of 2 or something like that.
Okay,
Yeah.
thank you.
Thank you.
Okay, we have one more question in the back there.
Okay, thank you. Susan Mumfler, University of Bern. I was wondering if you could elaborate a little bit on why you argue for isotope exchange reactions for carbon instead of photochemistry, because there's now more and more evidence that the sun is also isotopically light in carbon, so we would need a process that very effectively fractionates carbon between the solids and the gas phase.
So what is so I do not answer what's your point. So carbon isotope exchange reaction is also important for carbon isotope fractionation, you mean?
Well, it could be. I mean, that's why I'm trying to understand why you argue for low temperature chemistry instead of photochemistry for carbon fractionation. Or you even said that there was hardly any carbon fractionation in the solar system, which I believe is not true.
Yeah, I don't know why the solar system body do not show significant carbon fractionation, but so yeah, we will discuss later, I think. Yeah.
Okay.
Sorry.
I think they do actually. If the sun is at around 120 and then the Earth and other bodies are at 89 or so, the comet is even a little bit lower, then we would have some significant fractionation.
Okay, thank
But
you.
we can discuss later. Thank you.
Yeah, okay, thank you.
Okay, that could be the difference between solar system and what astronomers think is significant. Let's see. So I don't see any more questions, so let's thank the speakers again for a very nice talk.
Thank you very much.